Welcome back, AP Stat. This is Chapter 20, Hypotheses, Significance, Error, and Power. This is my title for this chapter. The book has a different title, so you can see which one you like best, but the book does a great job dropping a lot of terminology and a lot of concepts that you need to know into this chapter and weaving them all together quite well. So we're going to go through this chapter and we're going to learn a whole lot. So, to review, let's look at the possible alternative hypotheses we could run into. This is a familiar problem. Suppose researchers are trying to determine the effectiveness of some pill for the common cold. They're interested in the proportion of people who could kick their cold in 8 days. That is about the average time it takes for an adult to be entirely rid of their cold symptoms. So let's suppose that 50% of adults with colds are rid of their symptoms within 8 days, while 50% have symptoms that linger on past that 8-day threshold. If doctors were curious as to whether the pill made some kind of difference, whether good or bad, their hypotheses would look like this. Null hypothesis P equals 0.5 and alternative hypothesis P is not equal to 0.5. So the P sub 0 value would be 0.5. So P is the proportion of people who are through with their cold symptoms within 8 days. So this alternative hypothesis is known as a two-sided alternative, since we are equally interested in deviations on either side of the assumed proportion, which in this case is 50%. If doctors were curious, instead, as to whether the pill helped relieve people's symptoms quicker, so there's a clear direction for our alternative hypothesis, their hypotheses would look like this. So we have our H sub 0, our null hypothesis, P equals 0.5, same as before, but our alternative hypothesis is P is greater than 0.5. So we're testing with our alternative hypothesis the proportion being greater specifically than 50% of people kicking their cold symptoms within 8 days. This alternative hypothesis is known as a one-sided alternative. This is what we would call a right tail test. We're examining the right tail of the bell curve, but generically it is a one-sided alternative since we're only interested in a deviation on one side of the assumed proportion, one side of our P sub 0 value, in this case 50%. So we're going to be writing some one- and two-sided alternatives. We're going to be making sure we really understand how to write alternative hypotheses. Null hypothesis is pretty easy. Alternative hypotheses, those are interesting. So, suppose Mr. Clymer claimed that 2% of the transactions in the lunch line involve students who forget to load lunch money into their account and have to settle for a beggar's meal, aka the IOU sandwich or the PB in debt. The lunch staff isn't so sure that Mr. Clymer's proposed P sub 0 value is correct. By the way, I'm working on a trademark for the IOU sandwich or the PB in debt. I'm especially fond of this one, so trademark incoming. So if the lunch staff were concerned about any significant difference from Mr. Clymer's guess, then their hypotheses would be H sub 0, null hypothesis, P equals 0.02, and H sub A, alternative hypothesis, P is not 0.02. That would be a two-sided alternative. We'd be analyzing both sides of the normal model. If the lunch staff were concerned only about a significantly higher proportion of students who forget their lunch, their hypotheses would be P equals 0.02 for the null, and P is not the not equals, but specifically greater than 0.02. And we would only be working with the right side of the normal model. Okay, so you have one- and two-sided alternatives in reverse order. So now we're going to take this a step further and talk about the level of significance. This helps us to understand how precisely we use our normal model to help us make decisions with hypothesis tests. So how small does the p-value have to be to reject the null hypothesis? What makes a difference significant? All right? What makes us reject the null hypothesis? Well, it depends on the level of significance required for the scenario. Alpha, that little A figure there, A looking figure, is called the level of significance. And A is the upper bound of the set of p-values that would be deemed significant. We look for a low p-value to reject the null hypothesis. How low? Well, it needs to be under alpha, all right? Alpha is the upper bound of the set of p-values that would be deemed significant. If the p-value is less than alpha, then we reject the null hypothesis. The lower the value of alpha, the more unusual, therefore, our results would need to be, that is relative to the null hypothesis, to deem them significant, all right? What is the p-value? It's the probability of getting results like ours if the null hypothesis were true. So the lower the value of alpha, the higher the demand on the data to be really different upon analysis. Common values for alpha are 10%, 5%, 1%, and as low as 0.1%. And technically you can go lower than that, but those are the ones that we generally see at this stage of the game. Letter A depicts alpha for a one-sided alternative, while B depicts alpha for a two-sided alternative. So we have an area on the left-hand side over here that is specifically on the right tail. It might as well be on the left tail, but it's a one-sided alternative, whereas on the right-hand side, we have another bell curve with area on both sides. That is a two-sided alternative. So that shaded part represents alpha, a probability of getting especially unusual results. So, let's go back to a prior scenario. Suppose the example from the last chapter about sex discrimination at birth were alpha equals 0.05. Remember that our p-value was 0.0146. It was about 1.5%. So, would our result be statistically significant? Okay, well, here's the question. This is alpha. Here's our p-value. Is the p-value below alpha? It is that simple. The answer is yes. 0.0146 is less than 0.05 last I checked. Therefore, what conclusion should we make about the null hypothesis? Well, if the p-value is less than alpha, we reject the null hypothesis. That is what significance means. Is the p-value below alpha? If it is, if the p-value is below alpha, the level of significance, we reject the null hypothesis. Our data are significantly different than the null hypothesis predicts, so we reject it. So, next question. Would our result be statistically significant with a more rigorous alpha of 0.01? Well, we ask ourselves, how does alpha compare with our p-value, right? Well, alpha is below our p-value, so our p-value is not 0.01, or rather less than 0.01. Our p-value is greater than 0.01, so we do not reject the null hypothesis, which is the answer to this last one. Alpha equals 0.01. What conclusion should we make about the null hypothesis? Do not reject it. The p-value is not less than our level of significance alpha, so we should not reject the null hypothesis. So we see here a little bit of a push and pull. We set alpha. We determine what significance is for our study. So to an extent, significance is subjective. But in another sense, significance is objective, since a p-value is a probability brought to you by really calculus, integral calculus to be precise, but for our purposes, the calculator. It is a calculable probability, and that is objective. So there's a little bit of subjectivity on the part of the researcher and a bit of objectivity from the p-value itself. And that is a recipe for significance versus insignificance in a hypothesis test. Now we're going to talk about the relationship between significance and confidence intervals. As you can imagine, confidence intervals and hypothesis tests both fall under the umbrella of what we call statistical inference. Okay? So we should assume that they are related, and in fact they are. So suppose the lunch staff collected data and made a 95% confidence interval for the true proportion of transactions involving students who forgot their lunch and had to get the IOU sandwich, the PB and debt, or just let's call it a PB&J. First of all, to do this, the lunch staff would have to check off a couple boxes. Ensure transactions are independent. All right, so one person's forgetfulness or purchase or whatever is completely independent of anyone else's. And that's not a tough assumption to make. Select transactions at random, okay? So we could do a simple random sample of all transactions. That would be a little complicated to put together. Or we could do a much easier technique, not as good as a simple random sample, but systematic sampling. Start randomly with one student, maybe roll a die, and maybe it lands on 3. Okay, we start with our third student, and then we would proceed to, every 5th student, something like that. So we would need to randomize it in some way. And sample no more than 10% of all transactions, okay? So if we do this over the course of a couple days, that's way less than 10% of all transactions for the course of a school year. And sample at least 500 transactions, since n times p sub 0 would be 10. So we need 500 transactions. That could happen over the course of a couple of days, maybe a couple of weeks if we were to space out the days, maybe choosing days at random over the course of a month. But we could get to 500 transactions pretty easily, and that would be way less than 10% of all transactions over the course of the year. Okay? Assuming they accounted for all of this, which would be very impressive, awesome job, lunch staff, they could use their confidence interval to conduct a test with a two-sided alternative at alpha equals 1 minus 95% is 0.05. So you'll notice the connection between the level of significance and our level of confidence. The level of confidence and the level of significance are complements, right? So if we have a 95% confidence interval, we could use that confidence interval to essentially conduct a hypothesis test with alpha equals 0.05. All right, the complement of 95%. Our confidence interval says we're 95% sure the true proportion is in here. A significantly different proportion would be in the 5% on the outside. So let's talk about this a bit more. The lunch staff's 95% confidence interval is 0.023 to 0.035. This means we can be 95% confident that the true proportion of IOU transactions, people who end up with a PB&J and a bit of debt on the side, is between those upper and lower limits. Thus, we can be 95% sure that the true proportion of IOU transactions is different than Mr. Clymer's estimate of 2%. We could, even though we did not even find a p-value, reject h sub 0. You will notice that 2% is not within this interval, and we are 95% sure that p is within this interval. So this falls in the 5% of, the interval's probably not there. Or as in the proportion is probably not there, okay? So since this 2% is not in this interval, we can be 95% sure not only that the true proportion is in here, but that this 2% is outside of it, and we would reject h sub 0. In this way, confidence intervals can act in place of hypothesis tests for two-sided alternatives, specifically one-sided That's a little more complicated. But two-sided alternatives, honestly, in statistics, are preferable, and we'll talk about that a little more as we go on. However, there is something we lack. Without a p-value, we can't tell how unlikely the lunch staff's data would be if Mr. Clymer was in fact correct, which is often something that we want. We want to know how unlikely the lunch staff's data would have to be if that 2% prediction from Mr. Clymer were actually the truth. So, in short, given a parameter p and an assumed value of a parameter p sub 0, a p-value shows how unusual our data would be if p sub 0 were actually the true proportion. That is, if h sub 0 were true. So that is what a p-value tells us. That null hypothesis, what are the odds of getting data like ours if the null hypothesis were true? A confidence interval, on the other hand, says where p is likely to be. Those two are awesome separately, but they're even better together because we want to know where the true proportion is and how weird our data are if our initial guess were actually true. Those pair together quite nicely. So this means that for a two-sided alternative and a particular level of confidence, a confidence interval will contain p sub 0 if the p-value is too high for our result to be deemed significant. So if we get a confidence interval that contains p sub 0, our p-value for the related hypothesis test is going to be too high for our result to be deemed significant. Confidence interval contains p sub 0, do not reject the null hypothesis. However, a confidence interval won't contain p sub 0 if the p-value is low enough for our result to be deemed significant. So if our confidence interval, like with the lunch orders, the transactions that ended with IOUs, like that example, the interval did not contain our p sub 0 value. That means that the p-value is going to be low enough for our result to be deemed significant. So confidence interval does not contain p sub 0, reject the null hypothesis, we have a significant result on our hands. So we see some pictures as to what's going on. Here is a 95% area, and on the x-axis would be a representation of a 95% confidence interval. Say our p sub 0 value is somewhere in the middle. We would not reject the null hypothesis because our assumed population proportion is within the confidence interval. But if our assumed population proportion is outside the confidence interval, we have the green light to reject the null hypothesis. There's something unexpected going on because our confidence interval is over here, so we are not very confident in our p sub 0 value.